Hi everyone. In this video, we're finally going to talk about or describe precisely and completely how to solve this system AX equals B. Now, if you read the title here, I've written the complete solution to AX equals B. What does this complete solution mean? Well, if you recall in previous videos when we talked about solving AX equals B, we would ask, can it be solved? Would there be only one solution? Would there be many solutions? What are some conditions on the components of B that are going to guarantee that the solution exists? So in this case, what we are going to talk about is really discuss cases when the complete solution is in fact an entire vector space, so infinite but with structure, or if it's unique, meaning there is only one solution, or if there is no solution. So we will discuss those three cases through examples. But for the time being, so the first few minutes are going to be a bit theoretical, but after that we'll go completely into examples to understand everything I'm about to explain. So in the videos that we talked about, that we introduced yesterday, we talked about the null space solution, or the solution to AX equals 0. Now, if the matrix A is invertible, maybe I'll write that. So if A is invertible, and in fact there is a little bit more here, if each column of A is a pivot column, this is an important distinction. If your matrix A is invertible, then having each column be a pivot column implies, if your matrix A is square, then having each column be a pivot column implies that A is invertible. But the statement will be true even if your matrix A is rectangular, provided that each column has a pivot. So if each column of A is a pivot column, then the only solution to AX equals 0 is X equals 0. So only in the case when each column is a pivot column. Why is that so? Well, because remember, AX represents a linear combination of the columns of A. So when we have an X which is not 0, it means that there is a way to combine the columns of A that gives us a 0. That would imply that the columns of A are linearly dependent, which can only happen if we have at least one free column. So whenever the columns are each have pivot column, which means they're all, if each column has a pivot, which means all columns are linearly independent, the only way to combine them to get a 0 is if we multiplied every column by a 0. That's what this statement over here says. All right, now if that is not the case, so if there is some xn in, the symbol means in the null space of A, so let me say xn not 0, so some non-zero vector, because the null space of A always exists. It would always contain the 0 vector, but I want us to consider the case where we have more than the 0 vector, so something non-trivial, some linear dependence in the columns of A. Then, or rather, so if we have this, and if AXP equals b. So what is xp? xp is a particular solution that solves the equation ax equals b. This is a particular solution, and xn is an x in the null space. So if we have an x in the null space and if we have a particular solution, then xn plus xp also solves ax equals b. Why is that? Well, let's just multiply a by xn plus xp and see what we get. So if we do a times xn plus xp, what we will get is axn plus axp. Now a times xn is 0 because xn is in the null space of a, which exactly means that axn is 0. And we assume that a times xp is the vector b. Then the sum of the 0 vector plus the vector b is the vector b. So we see that xn plus xp is also a solution. In other words, any non-trivial vector in the null space of A will give us a new solution for the equation ax equals b, provided we have one particular solution. And I say one particular solution because we get all other solutions by adding vectors from the null space of A. So in other words, our strategy for finding the complete solution, so the complete solution would be this expression actually, where we say xn could really be just anything from the null space of A. The strategy for finding the complete solution would be, so maybe I'll write it on a new page. The strategy for finding or describing the complete solution to ax equals b will consist of the following steps. So first will be describe completely the null space of A. How do we describe the null space of A? So here are some steps. Find all special solutions. To ax equals 0. And we get that by reducing to rx equals 0 or ux equals 0. Both would be possible, but for today let's stick with rx equals 0. So I'll just write that is all special solutions to Rx equals 0, where R is the reduced row echelon form of A. Right? R is the reduced row echelon form of A. And the second step will be to find one particular solution to ax equals b by finding one particular solution to Rx equals D. We normally wrote Ux equals C, so we need a different letter to highlight the fact that R and U are not necessarily the same matrix. Sometimes they could be if the matrix A has the appropriate numbers, but it's not usually the case. So we carry out more elimination on A, therefore we would change that vector B from C to D. And you will see through examples that once you have the form of the matrix R, or once you use the reduced row echelon form of A, it's very, very easy to find a particular solution to Rx equals D using only the pivot columns. So maybe I can say that we'll use only the pivot columns of R. Now, it is not necessary to only use the pivot columns, but it would be the easiest because we are only trying to find one particular solution. We don't need all of them. We don't need 5. We only need one. Once we do that, then we have the entire solution. So then the complete solution will be, so let's say you have special solutions, I don't know, let's say you have 3 of those, x1, x2, x3, or you have x, y, z. Then the null space will be the space of all linear combinations of the special solutions. Or maybe I could even call those special solutions S1, S2, S3. So let me put here the special solutions. Let's say they are S1, S2, S3, for example. There could be more, there could be less. Then the null space of A is the set of all combinations that contain C1, S1 plus C2, S2 plus C3, S3, where C1, C2, C3 are some numbers in the set of real numbers, or just some scalars. So you see the general form, general expression of the null space is this. You can actually combine the special solutions to AX equals 0 with, you can take their linear combinations. And any of their linear combinations is going to be another solution of the null space. So then the complete solution to AX equals B will be the null space solution. So X will be the null space solution plus the particular solution, where the null space solution is not just one vector in the null space, but really all of them. So it will be C1, S1 plus C2, S2 plus C3, S3. So this whole thing is a general expression of a null space solution plus the particular solution. Now, it's very important. This particular solution over here, you cannot multiply it by any constants. That stays on its own. You just add the particular solution. How do you get from one particular solution to another particular solution? That is given by the null space. So if 2 of us found different particular solutions, we would still be describing the same x, because for us, for 2 different xp's, the different coefficients C1, C2, and C3 will correspond to the same solution x. So there is no need to worry about which particular solution we choose, but what is important is that when we write this general solution or complete solution, that we don't multiply the particular solution by any constant. The particular solution is just what it is, whereas the special solutions to AX equals 0 get multiplied by respective constants, because any linear combination of those special solutions is a solution to AX equals 0, or rather, all of their linear combinations express completely the null space solution. All right, now we'll put all of this strategy in practice through several different examples to see the different cases that we could have, but I'll do that in following videos.